All right, so it looks like we got a lot of participants in here today. We're going to go ahead and start introducing the webinar. My name is Chris Smith. I work at ACCI Specialty Materials. I'm a process development scientist here. I direct the research and product development, and I'm part of the Materials and Extreme Environments Committee here at SAMPE. So we've been working hard organizing these webinars to try and put them out every few months, just to get people together, people that have like interest, talking about issues and problems and opportunities in this field of high temperature composites. So as part of that, we've been reaching out to professionals in the field, looking to open opportunities to give webinars. So we're lucky to have Professor Stewart today. So welcome. So SAMPE has made these technical committees in the last couple of years. They've branched out to their community, and they've gave an opportunity for people to join into one of these divisions and help kind of expand the field and expand the collaboration in this area. So there's 5 divisions. We've got advanced manufacturing, bonding and joining, materials for extreme environments, which is this month's webinar, sustainability, and thermoplastics. So if you have interest in joining this community, we have a LinkedIn-like website called SAMPE 365. You can go there and create an account, and you can see these discussions. So there's a link there, 365.sampe.org. We'd love to have people sign up and join the community. So the high temperature materials leadership team, there's 4 of us at the moment, and we're always working on growing. So the chair is Tanea Mendel, and she's a grad student at Texas A&M. And the vice chair is Dr. William Guzman. He's a materials engineer at Renegade. I work at ACCI Specialty Materials in Kansas City, and our other co-secretary is Jaden Palick, and he's at the University of Lincoln, Nebraska. Every year, we're working on putting out a State of the Technology Industry report. There was one put out last year, and it's accessible to everyone for free. And we're working on this year's report, expected to come out late May. But you can download this at the SAMPE store, make an account, download it. It's free to get a sample, to download the report. And we are open to contributions from all over the SAMPE community of contributing to these technical committee sections that put together the State of the Technology report. Just a little bit about membership at SAMPE. So if you have anyone you know might be interested, you can contact Ms. Kelly Chin at her email address is right there, kellyc@sampe.org. Like I said, it helps provide a technical community for people to come together, discuss what their problems are, hopefully collaborate on some issues, and connect people who are looking to maybe help with testing or helping with formulation or pre-pregging, all sorts of things. So it's a large community. There is a SAMPE journal that comes out every couple months. It's a very high quality journal. I suggest, if you haven't read it, to look at it. It's a very good journal. And of course, we have the conferences. So the next conference coming up is going to be in Long Beach. So conference May 20th to the 23rd. So we look forward to seeing everything new that's happened over the past year. 4,000 plus attendees, so it's a fairly large conference, and it's a lot of fun. We have a couple webinars coming up. April 17th, we'll have the simulation of thermoplastic composites forming with the Thermoplastic Technical Committee. And on the 30th, we're going to have a SAMPE Tech briefing that's going to be open to the public. So you can see some information on April 30th. There'll probably be an email come out. This is going to be the leadership team talking about the state of the of the group, and it's open to the public. So the reason we're here today is to listen to Dr. Calvin Stewart talk about some interesting research. So he's in the College of Engineering Innovation Scholar, and he's the assistant professor in the Department of Aerospace and Mechanical Engineering and the Department of Material Science and Engineering at Ohio State. He got his BS and his master's and his PhD in mechanical engineering at Central Florida. And he currently directs the Materials at Extremes Division at Ohio State. So his current research involves low-cost additive manufacturing of superalloys and refractory alloys for extreme environments, develop of accelerated, parallelized, and miniaturized testing protocols for new materials qualification, and the development of probabilistic machine learning and advanced models for the mechanics of materials in extreme environments. Dr. Stewart's authored over 80 papers and has generated over $11 million in research grants, coming from the Department of Energy, the Nuclear Security Administration, Nuclear Regulatory Commission, Honeywell, MF&T, and the Air Force Research Labs. So it's my pleasure to hand it over to Professor Stewart. Thank you very much for coming today, and we look forward to it.
Yeah, thank you for the warm introductions, Chris. Let me share my screen and we can get started. All right. So thank you all for attending today. You could have been anywhere, but you're here with me. And today we're going to talk about materials at extremes. I'm Dr. Stewart. I'm an innovation scholar in the College of Engineering. I've been at the Ohio State University for 2 years to lead this initiative around materials at extremes. Our initiative, our group, is focused on cross-cutting research that sits at the intersection of different domains of science. There's 3 pillars of excellence that we focus on. One is advanced manufacturing, where we're looking to leverage things like additive manufacturing, like friction stir welding and other new techniques to both discover new materials as well as design unique components that can survive extreme environments. With these new materials that we make, we then need to figure out how to test them, how to make sure they can survive those environments. So we also focus on developing novel, advanced test methods that allow us to more rapidly screen the resistance of materials to extreme environments, to create tests that mirror the real world rather than the laboratory that they would usually be conducted in. And then finally, with the results of our experiments on our custom materials, we then explore those extremes, explore the response of materials at these unexplored domains, and develop new equations, new theories, or new ways of predicting the response to extremes. So for me, much of my research, I like to think on a high level. I like to think about what's motivating us. What in society are these environments where we see extremes? And at the current place we are in society, the extremes are pretty extreme. Whether it's hypersonic vehicles flying at 5 to 8 times the speed of sound with combustion temperatures over 3,000 degrees Celsius, or whether it's liquid-fueled rocket engines, your SpaceX's of the world, who are burning at over 3,000 degrees in their combustion nozzle and burning for about 8 minutes to get to orbit, and maybe flying multiple missions, to jet engines, to our fighter aircraft that are subject to flight dynamics and have turbine entry temperatures exceeding 1,800 degrees Celsius, or even the low temperature but still extreme industrial gas turbines, which are subject to 1,400 degrees Celsius and can be asked to survive and operate for up to 30 years or more. In all of these 4 use cases, these are materials that are being asked to survive above the base metal melting temperature. Nickel superalloys melt around 1,200 to 1,300 degrees Celsius. So in every one of these cases, the base metals or the base materials we use would actually melt in reality. And so what do? We take our monolithic materials and we coat them in thermal barrier coatings. We core them out and install internal cooling passages. We may even bypass air across the skin of these components to create a cool layer that keeps them from melting. But in all cases, we are beyond the limits of the material's capability. So how do we push? How do we get to 4,000 degrees? How do we push beyond these limits? How do we increase performance? Is the question that my group is really interested in answering. Now, there's two kind of pillars or places that we sit in development of new materials. One of them is the concept of the materials genome initiative. This concept that we can computationally design from chemistry from chemistry, we can predict structure. From structure, we can predict properties. And from those properties, arrive at performance in extreme environments. But there's a lot of steps in this material genome initiative that we have to step through, from the computational, from basic computational thermodynamics and molecular dynamics, to then making the material, from using additive or small scale arc melting to create small samples, to then post-processing, thermomechanically processing materials to arrive at a good structure, to then testing and qualifying the performance of those materials and components. What my group sees is that there exists a bottleneck. There exists another step that is needed to accelerate the materials genome initiative. And that is this idea of developing rapid screening tests, where we can take very small volumes, very small samples. We can take samples and get parallelized information, get more than one test out of a sample in order to rapidly screen the resistance of these candidate materials and tell us, should we go back to the drawing board? Do we need to go back to chemistry? Or can we actually proceed with the very expensive qualification that's required to get to service? And in that need, if we think about additive manufacturing specifically, the costs for qualification can be quite high. There's installation qualification of your equipment being installed. There's operational qualification, which is getting just baseline ability to print a material, to print the material of interest, just to get it fully dense, to get a baseline microstructure before you post-process, to then moving to performance qualification, where you actually start printing parts, you actually start making things. When we add up the costs or the timeline for deploying from chemistry to part, the costs as well as the timeline is extreme. And we believe that accelerated tests and new methods are needed to get us on pace with the rate that additive technology is evolving. So with our motivation down pat, we're going to today go through our three cross-cutting areas of research. We're going to talk about advanced manufacturing and some of the cool things our group is doing. We're going to talk about advanced test methods, and then we're going to round it out with theory. I'm going to hit you over the head with a few equations at the end, right? So let's start with advanced manufacturing, and we're going to start with low-cost metal additive. My group has been working for the last few years on a metal additive technology called bound metal deposition. It's a technology where you take metal powder that you would usually use in laser powder bed fusion or directed energy deposition, and you coat that powder in a binder additive and polymer to create a filament. The same type of filament you would use, say, in a MakerBot or a Bamboo Labs machine, right? The enthusiast 3D printers that some of you have at home. The beauty of this is that now the cost to actually deposit material goes from $100,000 or $200,000, it depends on your printer for your laser powder bed fusion, to $1,000 to print a basic part, right? That is metal. So it's an incredible capability. The downside, the challenge is the research for bound metal deposition comes from how do we then go from this composite filament of metal and polymer to a part that is fully metal. And that's where we need to develop the debinding and sintering technology to create fully metal and fully dense parts. Now, our group has been, playing around with this for a while. We work with a small woman-led business who actually has a proprietary technology where they create these filaments. And we've been exploring a variety of alloys and the limits of what we can do with bound metal deposition. Whether it's 3D printing tungsten hypersonic leading edges, or even multi-material prints of a leading edge with an internal titanium rib structure, to then creating even full-scale impeller parts that are used in UAS, unmanned aerial systems, JetCat type of UAS engines. So we've done a lot of the demonstration work to develop print parameters so we can get good quality prints. But the newest thing that we're doing, and something that we're really leaning into, we've got a new project coming online, should be announced any day, is this idea of leveraging bound metal deposition to enable metal additive manufacturing in space. Right now, we are literally sitting on the cutting edge. Just recently in January, a module was launched to the ISS that enables kind of a melt pool based metal additive manufacturing. The first metal additive manufacturing hardware was sent to the ISS just this year in January. However, FDM, your MakerBot type printers, have been on the ISS for well over 10 years. Specifically, the Additive Manufacturing Facility, the AMF, that sits in the Destiny module on the ISS. They have been FDM printing various polymers, over 100 different tools and objects for well over 10 years. So we believe that we can leverage bound metal deposition, the filaments, and be able to print metal in space with hardware that's been there and has been proven for a long time, for a decade. In addition, there was another a device, a low gradient furnace, that would allow us to do vacuum sintering to actually debind and sinter our BMD parts to create fully metal, really useful tooling on the ISS. And so between these two devices, we're working, we currently have funding with Air Force Research Lab to demonstrate this technology in the laboratory. And then we're working on a proposal to the ISS National Lab to actually launch some of this filament, as well as some of our demonstrators to be debound and sintered, as well as printed on the ISS. It's really, really cool cutting edge things. Now, where can this kind of lead? Where can this technology lead? One thing is on orbit surface assembly and manufacturing. If we can make metal parts in space, then we can repair satellites. We can print structures. Perhaps we can even, given a big enough space-based FDM printer, print spacecraft using this technology, right? Very cool stuff. Another area that we're interested in for advanced manufacturing is this idea of multi-material or multi-metal additive manufacturing. Right now, most of the additive parts that are being printed and even deployed in various fleets are made of monolithic materials. We have one powder, say we have a titanium powder or an Inconel powder. We fuse it using lasers or electron beams, and we create a monolithic part that is made of one set of chemistry. And yet, most of these additive technologies do have the capability to blow different powder mixes or to deposit different types of powders right next to each other and create multi-metal parts. So what we really want to do is develop a framework to enable design for multi-metal additive manufacturing, where we can create parts that have different strengthening materials to resist different forms of attack, whether it's cracking, creep deformation, whether it's literally depositing a thermal barrier coating while you're printing the base metal, or even resisting irradiating environments, right? This opens up our ability to do spatial materials design, to do generative design or topology optimization and place material strategically where you would want it. So to start it out, my group, we believe in demonstrators. We say, hey, this is easy to do on FDM. Just about all the FDM printers that you buy nowadays have the ability to print multiple filaments. So let's make a demonstrator of what our goal is, this multi-material turbine blade, and then let's step through the process, develop a design framework, as well as address the problems or challenges, and then we'll move to metal. So for multi-material or multi-metal additive, what are the advantages that we get? Well, we gain the advantage to lightweight parts by reducing the thickness of those monolithic materials and replacing critical regions with higher strength, higher ductility, or more wear-resistant materials. When combined with additive manufacturing, we can also create parts that have hierarchical structures, periodic structures, or lattice structures that further lower the weight, but give you kind of multifunctional responses in your parts. And with the technology advancing, we'll then be able to lower the weight, lower the cost of parts, and increase their resilience and resistance to extreme environments. Our current study on this focuses on notch strengthening, a very traditional and conventional challenge. When you design a part, you have some complex shape to it, a notch, an edge, stress concentrates. And some materials are resistant to stress concentrations, and some are not, which can affect your ability to design a thin or part. So we've thought of a couple of concepts, whether it's section replacement, completely removing a section and replacing it with a higher strength material, or even being smart about it and using computational tools to design the placement of material to track stress or strain fields. Or furthermore, for surface-based effects, skinning a part, developing skins that protect from wear or crack initiation resistance, and then transitioning this design for additive technology to the various types of additive manufacturing. So what have we done? Well, we started from the old school. We developed analytical tools, maps, that help us to design a notch-resistant part that's multi-material. Then we moved to the finite element analysis to match and determine if our analytical solutions and design approach matches what we would expect in the simulated world. And then finally, we developed a test framework and a test method so that we can then assess if our analytical and computational matches the experimental. From there, we moved to testing on our FDM prints of multi-filament type of tests. So testing samples of 2 different filaments that have a different stress strain response. And we found that our analytical and computational predictions match what we expected in the real world. But furthermore, that we found that we had no stress concentrations at the interfaces, that if you select the right build parameters when you're printing your part at the interface, you can avoid any interfacial strains or mismatch. Really cool stuff. So now we've moved from the polymer-based science to moving to that multi-metal-based AM. We're working with this company, NIDAC America, doing directed energy deposition, blown powder, multi-metal additive manufacturing. And at the current point, we've created some bars that are a combination of 316, our weaker material, with Inconol 718, our nickel-based super alloy. And at this point, all we got to do is cut them and repeat our test methods to prove out this new design for multi-metal additive manufacturing approach. Now from this, we've got a lot more steps to make. We've got to go from just doing notch strengthening to saying, well, hey, what about high temperature? We're trying to get to extremes, right? What happens when we take this to 1,000 degrees Celsius or 1,400 degrees Celsius? What happens when we subject it to dynamic loading conditions and crack initiation, fatigue crack growth may be a concern? What happens if we take it to super high hertz and we start to have things like wear resistance occur? Can we develop a framework for different types of strengthening, design for different types of strengthening, and then integrate that in some computational tool to enable generative design, AI-based design of these multi-material regions that strengthen an overall part to form multiple forms of attack? It's a lot of potential there, right? A lot of potential outcomes. So now let's move to the second pillar in our group, and that's this idea of advanced testing. Now, my group, we touch a lot of different types of testing. So we do rapid testing where we time accelerate. We try to shorten the duration of tests. We do parallelized testing where we try to capture multiple streams of information from a single sample. And then finally, we try to develop intelligent tests, tests that have rules, but also machine learning-based controls in order to run autonomously, right? We don't have enough time to touch all of them. So today we're going to focus on parallelized testing, right? So before we go into these advanced tests, let's talk about a standard test. Standard tests for materials to assess their properties at extremes are usually based on a testing standard. There are various standards around the world. There's ASTM International, there are ISO standards, there are French standards, British standards. My group, we focus on the ASTM International, right? In standardized testing, the goal is to produce a result that is repeatable, meaning if you test multiple times, you get the same answer, and reproducible, meaning if a different lab around the world tests, that they are also able to reproduce the same results. Because of that, you have to develop very stringent requirements for every test that you run. And because of those requirements, you need to also run many, many repeat tests in order to qualify the uncertainty of your test methods. So specimens need to be subject to uniform temperatures with very tight tolerances of plus or minus 2 degrees Celsius. You need uniform stress, both in the design of your sample, but the alignment of your load chain. You need to calibrate your system to know the accuracy of your load cell, your thermocouples, your extensometers. And then you need to repeat your tests multiple times and get your standard deviation, your mean values. All of this then leads to you needing to do tens to hundreds of tests for any particular material of interest if you're subjecting it to extreme environments, ranges of stress and ranges of temperature. Because of that, it is very expensive to qualify new materials for service. If you make a new chemistry, you want to say, hey, I want to put it on this airplane. Well, guess what? You got 10 years of work to do before you can fly that material. So what our group is doing is we're leaning into moving away from the standards. We still believe in the standards. We don't want to toss them away, but we wonder if we can develop rapid screening tests and use newer technology that allows us to get information faster in parallel and be able to screen to say, you know what? Let's make a bunch of different chemistries. Let's run one test over a range of conditions, and then we can determine the optimal chemistry to spend 10 years on. That's the goal. That's kind of what we're focused in on. So to do that, we're using this technology called digital image correlation. And we're doing a special version of it. We're using infrared cameras, so infrared. We're using 2 white light cameras, so it's 3D, and then it's digital image correlation. This technology allows us to track a speckle pattern that exists on the surface of our samples that we apply to it, and to be able to back out the displacements, as well as the calculated strains from those displacements in 3D on the surface of these samples. With the infrared camera, it also allows us to gather the temperature on the surface of the sample and then be able to measure thermomechanical strains in extreme environments, to look at the effect of stress and temperature and strain, gather all of that information as a matrix of data rather than 2 points in one line, right? Now, there's some challenges in this technology. There's science to it, but there is some degrees of art. Whether it's applying the speckle pattern and making a speckle pattern that can survive 2,000 degrees Celsius. Not easy. Whether it's the calibration of the cameras so that we can get the Z dimension to understand what out of plane dimension is, or even to filter the light, to saturate the sample with a certain wavelength, the blue wavelength of light, to filter down to certain wavelengths that we see into our monochromatic cameras so that we can cut the glow of samples, of rocket engine samples, and be able to see their strains. Now, as we overcome all of those challenges in this new technology, it enables us to get some very interesting information. One duo of tests that we've been developing, we call the gradient boundary condition tests. These are tests that, instead of following ASTM standards and having stress, having a uniform sample for one value of constant stress, or whether finely tuning our temperature to have a set constant temperature in the vicinity of the sample. Instead, we use what the real world gives us, stress gradients and gradients of temperature. That's the real world. And if we can map those gradients, if we can design a sample with a bell shape where we can calculate what the stress is as a function of area, and we can capture the strain along those different values of stress, well, guess what? We just developed a test where we can get hundreds of individual conventional tests from a single sample. Make one sample, get 100 test results, right? But furthermore, say we make a specimen with a uniform gauge section, so one value, constant stress, but we design the temperature environment so that it is a temperature gradient that is quasi-static. So there's a gradient, but it's stable. Then we can get a temperature profile that changes along the sample, and then we can take little mini strain gauges across the correlations that we have and get 100 test results, again, from a single sample. So this parallelization, this massive ability to parallelize, takes us from having to do so many of these standard tests to say, you know what, this isn't a good chemistry, this isn't a good heat treatment, to be able to do 1, 2, or we'll say 5. Why don't we say 5 of these tests in order to screen the resistance of a candidate composition, right? Now, there are some limitations to this approach. One of them is that if we're going to test a part to failure, then we only have one critical location in our part, and that's where we will have a full test result, say a full creep test or a full tensile test. And everywhere else, all of our other points in the sample will only give us partial information about the resistance of the material. So we'll need to do some advanced modeling or theory development in order to predict those other non-failed responses. We'll get to that, though. We'll get to it. So in our lab in the last 2 years, we've built setups to do exactly these gradient temperature tests. Well, whether it's the Delta Sigma test setup, where we have 2 machines configured for this that can test up to 1,400 degrees Celsius with load capacities of 250 kilonewtons, that allows us to test these gradient samples. And we've machined some 4130 steel samples with a specially designed gradient for us to test and assess this technique. Or whether it's the Delta T test setup that we spent a lot of money building, but with very cool capabilities of testing with control to 1,800 degrees Celsius. If we're not careful, any metal we put in here, or just about any metal we put in here, is going to melt. If we're not careful with control, right? Now, if we go from pyrometer control to manual, if we switch to manual command, we're pushing 400 amps at between 100 to 400 kilohertz of frequency. So yeah, we're going to have a puddle if we're not careful here. We can melt just about anything. If we switch out our pyrometer, we can go to 3,000 degrees Celsius on this setup, right? Now, so this setup we specially designed a coil to induce a quasi-static temperature gradient. So with pyrometer control, we can create those gradients that we want to see that are stable, and then we can test our uniform sample and pull out that data of 100 samples. Now, some of our early work here has been just in calibrating and designing speckles that can survive extreme environments, and then also working on the filtration of light so that we can keep correlation, so we avoid gaps in correlation. And then the final crazy test method that we've been leaning into and we built something for is what we call the delta M, the gradient material test setup. This is the idea to say, hey, if we can parallelize boundary conditions, if we can make stress a gradient or temperature a gradient, what about the material itself? What about creating functionally graded materials where we change the additive powder on the fly and subsequently change the chemistry layer by layer in a part? If we do that, if we're able to create components with these unique layers with different chemistry, then we can create one sample that, say, represents 10 or 20 different chemistries that we think that might be good candidates, and then run this correlation to determine, of those 20 chemistries, which one do we want to build those full bars on of? Which ones actually have the empirical evidence of goodness? Our computational models tell us that they should be good, but which one actually empirically, or which range of chemistry is the sweet spot that we should explore, right? So we've built another test setup we call Delta M that gives us a full field view of our sample from tip to tail, that also has very fine control on temperature, plus minus 1 degree Celsius, with this big window on it, right? So this setup allows us to test up to 1,000 degrees Celsius, pretty hot, not 1,400 or 1,800, but still pretty hot, with a load capacity of 50 kilonewtons. And so we can then configure this and be able to measure the strain on the surface and be able to determine in those regions, in those zones, which composition will survive. Now, finally, we've even thought, well, hey, if we're parallelizing a few things, what if we just parallelize them all? From a quasi-static temperature gradient to a bell-shaped sample where we know the force to a functionally graded material. Could we use this to do A/B testing between one material and another? Or could we use this as a screening test where we're trying to design a material for a specific range of stress and temperatures, and we want to determine for those specific conditions, is this material strong enough? Would it survive? Well, we can make this extreme torture tests for specific applications. Now, our lab here that we've been building, this lab has existed for 2 years here. We've built it over the last 2 years. Is pretty incredible. We've got 4 servo hydraulic load frames that allow us to do dynamic type testing in quasi-static, so we can do tension, fatigue, crack growth. We have 1 electromechanical machine that we use primarily for quasi-static and accelerated creep type tests. We can test from 50 to 500 kilonewtons, from room temperature to 1,000 to 1,400 to 1,800 to the melting temperature of your superalloy. And depending on our furnaces, we have heating rates up to 35 degrees Celsius a second. So in about 30 seconds, you're at 1,000 degrees. It's pretty hot, right? Just saying, it's pretty hot. And using our imaging, the wavelengths of light that we use to saturate our samples, the cameras, the filtering and optics, and multispectral imaging, we're able to capture the thermal mechanical response over a wide range of conditions, right? So very specialized. And I'm very proud of my team for all the hard work that we've put into this lab, from developing standard operating procedures to safety protocols. When you get to certain temperatures and you're using certain metals and there's certain powders, things like to melt, or metal can burn. I'll just say that. You can have metal fires. And so it's been incredible these last 2 years standing up this facility with unique capabilities. Now, the final thing I'll mention about advanced testing is, with all of these techniques, it takes a lot of human expertise and knowledge, from safety to the design of experiments, test matrix design, to programming the machines to operate safely and do what we want. Now, one thing that I'm really interested in doing, and I've talked with my team about, is this idea of combining this human knowledge we have, the rules and criterion that we already use to program our controllers, with machine learning's ability to detect responses and make decisions based on those responses. The question is, could we leverage the combination of human and machine intelligence to make autonomous some of these test procedures and these screening tests that take a bit of effort for my team to design and execute, right? So finally, we move to the last pillar, the final pillar of our group, and that is taking the results of our material manufacturing and our our novel testing, and develop theories that tell us how materials respond in these extreme environments. And that's advanced theory development. Much of our work has to come through the development of software tools. With the data that we generate, whether it's conventional ASTM tests or 3D digital image correlation, where we have matrices of data at every capture point and images for every multiple images for every capture point, we have to develop software tools to regress, to clean our data up, so it becomes something that we can use, right? So multiple language, whether it's Python, Fortran, or even integrating finite element code such as ANSYS and Abacus, so we can do digital twin simulation, so we can match the experiments to the simulations and see if the models are real, if the models that were designed 50 years ago actually capture the real world. So many of them don't, right? From that, we do things from data processing, create libraries of conventional classic models, develop ways to automatically calibrate models, different integration schemes, and digital twins of fulfilled measures. Over the last 10 years, my group has developed a number of equations that we've learned from our experiments. One of the more modern, and I would say probably the more impactful equations we developed, is the Wilshire-Kano-Stewart model. It's a model that integrates the modern Wilshire equations for creep rupture, which are very, very popular, have kind of become the new de facto over Larson-Miller, with continuum damage mechanics, so that we can both predict stress rupture, we can predict minimum rate, but we also can predict the creep deformation and damage evolution within materials, right? What's even cooler about this is some of the very newest stuff that we're currently in the process of publishing is using strain energy density dissipation, SED, as a measure of damage to pin down the calibration of the parameters in these types of models. So we've had some incredible outcomes with this model. Another new model that we've developed and we'll be presenting at Turbo Expo this summer is a threshold-based model. Often in creep flow, there's a question of at what stress levels do you have an infinite life? In fatigue, we have the endurance limit. We know it. We can test for it with a rotating bending machine. But in creep, we can never reach the endurance limit. Infinite creep could be 1,000 years of testing, literal 1,000 years of testing. So we've developed this threshold-based model that helps us to pin down a more physically realistic estimate of what that threshold stress should be, right, compared to other models. Now, moving from these models we call deterministic, we want to move, we know in our experiments, when we run them, that there's uncertainty. If we run the same test 5 times, we get 5 slightly different answers. So we ask ourselves, if we use deterministic models that only give us one answer, are we designing properly? Are we designing for the probability of failure, or are we designing for the average life, a potential life of a part? So what our group has done for theory development is look at what are the sources of uncertainty in our test methods, whether it's the boundary conditions during testing, variations in chemistry, processing, and defects, and how do we integrate those into our deterministic equations to make probabilistic predictions. And so we've used things such as Markov chain Monte Carlo so that we can take the results of 5 at minimum tests and then simulate thousands of variations based on the probability of failure of those 5 experiments, giving us an ability to rapidly screen and have the probability of failure, designed for probability rather than the average with big safety factors. From there, we've started to explore things like temporal uncertainty. What happens with fluctuations with time? To spatial uncertainty. What happens when you print multiple samples as you have different defects depending on where those samples are built on your build plate? Well, could those uncertainties be a source of the cause of failure at different times and a crack initiating and cycles to failure changing? So that is a very, very interesting space that we're exploring. But furthermore, machine learning. It is the new tool. It is the new tool in the toolbox. And you are doomed to fail if you choose not to learn these tools. Some people believe that machine learning is a tool that shouldn't be used, that it is a tool that leads to people lacking or losing their understanding of the fundamentals, of the science, of the theory behind things. But I'm a firm believer that tools are only as good as the hand that holds them. Say in the 40s, all design was done analytically with humans as calculators, right? The rise of the computer allowed us to use computers as a crutch, right? So we could do calculations using a computer. The rise of finite element analysis has now allowed us to then design parts and figure out stresses and strains and complex geometries using a computer as a tool. And even further, the rise of generative design and topology optimization has allowed us to let the computer design the part itself for us. However, we still have to have a human involved to determine if the outcomes of those tools we use will survive contact with reality. We still have to have an understanding of the fundamentals. And so our group is leaning into using machine learning to aid us in the discovery of answers that are hard for us to answer with our own domain of knowledge. One of the things we've done is look at black box machine learning, your neural networks of the world, and apply various different neural network-based algorithms in order to connect chemistry of materials directly to their performance using these black box AIs, so that we can try to then predict the chemistries that will improve the resistance of materials. We've been able to do testing, training data sets, and then compare them to post-audit validation, separate data sets that we hold hidden from our machine learning, and been able to make reasonable predictions of those hidden data sets of performance of materials. But the problem with black box is there are some levels of human interpretability that it lacks. We can't understand with black box how it actually makes the connection between chemistry and performance. It's something that's not opaque to us. It's something that can be a page-long polynomial chain that's hidden from us in our algorithms. So one thing my group's leaning into, an area of research that not many people are doing, something that we think is very cutting edge, and we are very much on the edge of publishing this, is the idea of using glass box artificial intelligence, AI that is opaque, that is transparent to the user, that a human can interpret, and we can use mathematics and science to accept or reject the outcomes of that AI. We are in essence pairing the human's expert knowledge, our inspiration and ability to work with small data sets with machine's ability to look at highly complex multivariable problems and to give you a high throughput. We're using this algorithm called multi-gene genetic programming with symbolic regression that allows us to genetically engineer equations that we can perceive and accept or reject as physical facts or phenomena between our variables, right? So the human and the machine connect at various spaces. We believe, and I believe, that by using this technique, we can encapsulate and close the material science pyramid. We can take chemistry information and connect chemistry to structure. We can take chemistry and go directly to performance. We can take chemistry to properties or chemistry to processing. As long as we have identified, us humans have identified the proper inputs, and we have some understanding of the physics and the connections between these pillars, we can create reduced ordered reduced ordered equations that connect different domains of science, right? Very interesting stuff. Now, in order to use these algorithms, any machine learning or AI, the human must actually train and control the way that those algorithms execute their operations. For multi-gene genetic programming, there's a lot going on. There's initial seed population. They make some babies. We do a calculation on how good those babies are. We build the next generation, another population. And then we seed populations across the globe so we can try to get a global solution where every parent and child is literally an equation. From seeding multiple populations around the world and evolving and genetically engineering them, we create a Pareto front of elite individuals, elite equations that we think have good characteristics, looking at the combination between equation complexity and the coefficient of determination, the accuracy of that equation. And then as the human, we have to screen of all of these elite equations, which ones are realistic, which ones don't violate physics, have dimensional homogeneity, are things that we can accept or that scientists may accept. But furthermore, when we're mixing different domains of science and generating these equations, sometimes we have relationships that would be good in one domain. Oh, these are good dimensions. And in another domain of the science are not allowed. So there's also these quandaries of going from chemical equations to going to mechanics of materials type restrictions on these equations. So in some of our current work, we've generated these equations. We've generated an equation connecting chemistry directly to the creep resistance of a material. And then we've done our test. We've done our evaluation of training and test data that we've calibrated the model to versus hidden data that the model never saw, and see that we get accurate predictions. And then finally, with this human interpretable equation, we can actually optimize the chemistry and design a chemistry that has extremely high resistance when compared to the chemistries of our experiments. We're actually able to find chemistries that have incredible capabilities. In fact, maybe this is a little too incredible. So to close the loop, what we've finally done, where we are currently at, literally right now doing, is using calculated phase diagrams, computational thermodynamics, to determine in our optimized chemistry, what structures are we actually forming? What is the difference? Why are we pushing out how are we improving our existence? Can we prove it via what structures form? And what we're finding is that with the optimized chemistry, we basically improved the stability of the carbides. Went from metastable carbides that change as a function of temperature from M6C to M23C6 to a stable M23C6 carbide that also has 100 degrees more capability, stability in terms of equilibrium, right? So in order to do all of this computational work, we use our Extreme Computational Lab, where we have high-powered workstation computers, and then we hook into the Ohio Supercomputing Center, where we're able to generate hundreds of millions of candidate equations using AI. So I've probably gone to a good point. We're at the end here. Thank you for your time and attention, and I'll be happy to take any questions from the audience. Oh, Chris, you're mute.
All right, sorry. Thank you, Professor Stewart. Very captivating talk. That was awesome. Surprise ending too. I like the twist with the AI. Very interesting. So we got a couple questions here. Just a reminder, if you do have a question, please type it into the Q&A chat box and we'll get through it. So I've got a couple in here now. So I've got great approaches. Congrats. Can you share the comparison test of the curved sample versus multiple samples with different diameters at a constant temperature? So I'm thinking maybe they're asking, how does the data of the curved sample look versus just measuring different samples of different sizes?
So that's a great question. And it comes down to time. For the curve sample, we're able to gather a lot of information in a single test. And these tests that we're running are creep tests. So these tests can take weeks to run a single test. So currently, we are generating the tests with our curve sample. And then after we've generated those tests and we've extracted the curves at different diameters, then we'll do the conventional ASTM type tests, which can take a very long time, which you can't do in parallel. So at the moment, we don't have those to compare. We'll get there, but it's going to take a lot of time.
Okay, and we've got another question here. In the multi-metal additive process, how does the final microstructure differ from standard casting processes?
So that's a great question. So in additive manufacturing, depending on the way that you are energizing, you are fusing your part, you can create very different microstructures. Whether it's laser powder bed fusion or directed energy deposition. For AM, usually what you want to do is you want to hip your part, you want to do hot isostatic pressing so that you can regularize the microstructure, removing the texture that you get from AM, and then you want to do a heat treat so that you can get retained strength in your part. And there's a number of AMS standards that have been developed for different types of AM materials. For multi-metal additive manufacturing, though, that becomes a challenge because now you have a material that has chemistry that's segregated in different regions. And when you go and hip it, and when you go and heat treat it, those chemistry, you have diffusion. You enable diffusion, right? And so that nice gradient chemistry that you printed into your part can become segregated. You can form deleterious phases. You can get cracking. And so the real challenge with multi-metal AM is, can you heat treat it? And the question is maybe, depending on materials compatibility. So for what we're doing with DED, we're not heat treating it. We're treating it as built. But in the future, it'll be something that we'll need to develop, such as, are there techniques we can develop to locally heat treat, to heat treat just distinct regions using something like our induction heater, to heat treat locally in certain regions at different temperatures to retain the strength you need in those microstructures? That's a great question.
See one more here. What specific aspect of multi-material additive manufacturing are you interested in learning about? So maybe the gradient materials, like what specific types of materials are you most interested in those types of samples?
Yeah, so for me, what I'm most interested in are domains where there already exist material joints. One of them is in liquid-fueled rocket engines. In liquid-fueled rocket engines, in most of your SpaceX-type companies, Relativity Space, SpaceX, NASA, they are doing multi-material, they're doing advanced manufacturing. So they're doing laser powder bed fusion to create a copper inner liner that shields your part, that allows for heat transfer, that prevents you from melting, right? And then they're doing DED to create an outer jacket around that copper liner of something like Inconel or a high-strength steel. So they are doing a two-step process of laser powder bed fusion followed by DED to create engines that are currently going to space, right? Now, in that process, it's two-step. You're going from one AM step to another, and the heat treatment is not possible. It's not possible in these steps. So I'm interested in those type of materials, which are materials such as GR-COP, which is a NASA Glenn developed copper alloy, Inconel 718s, your high-strength steels. Those type of interfaces are very interesting to me. Of course, GR-COP is one of those materials that's very hard to get a hold of. It's one of those materials synonymous with another material, GRX 810, another rocket engine material that is so new, you can't just go and buy it, right?
Yeah.
So to start, we're using something less expensive, 316L and Inconel 718. But we are looking for, we're also, I'm very much interested in your refractories. Hypersonics programs are coming online across the world. There are quite a few programs going on here in the US. And most of them, their key enabling technology is additive manufacturing. To print these refractory, high entropy alloys, they are leaning into AM. And guess what? You're not going to heat treat tungsten. You can't get hot enough. So the heat treat,
Yeah.
tungsten melts at well over 3,000 degrees.
Usually tungsten's used as like the boat in the thermal evaporator to hold the materials you're melting, not to melt them.
Yeah, it's your crucible, right?
Yeah.
But then tungsten is being used as leading edge material. Tungsten coatings, whether cold sprayed or whether 3D printed, tungsten heavy alloys are used as a skin for these vehicles. So there's a number of really interesting materials that I'm looking to play with.
Sounds good. I think we got a couple more questions. Time for a couple more. So what kind of distortions are experienced while doing infrared DIC, and how do you deal with them?
So that's another great question. In infrared DIC, we have challenges. One of the challenges is matching our optical cameras, which are at a very high resolution that have a high pixel density, to our infrared camera that has a much lower pixel density. So we're at 640 pixels with our infrared camera, and then our white light cameras are like 2,500 something pixels. So there are always challenges with how do you match the optics, and then how do you track those same pixel points. One thing we use lenses. We use focusing lenses that allow us to get closer to our field of view and have a field of view that matches both. Another thing that we use is we calibrate our infrared camera. We use the same calibration square for optical as infrared, and we heat up that square so that we can match the pixels, match points on that calibration grid between the white light and the infrared, and then correlate the same position in space, spatial positioning between thermal and mechanical properties. So it's challenging, but it's there.
Yeah, really dotting all your I's. So I've got one question. I saw a couple Instron tensile testers and some MTS. So did you have to work closely with some of these tensile manufacturers in developing this new equipment, or how were they with modifying this and making it fit for your application?
So that's kind of the beauty. These are universal test machines. Whether it's an Instron or an MTS machine, they're designed so that the user has flexibility, that you can control it in the way you want to control it. And so the real challenge was how to integrate the packages, the furnaces, the chillers, the sensors that I wanted into the space of these universal test machines. How to get the furnace in there, how to get the temperatures and controls. That wasn't easy, but I worked with third parties, with the furnace manufacturers. I worked with extensometer companies. Who I work with really the most is Correlated Solutions. Correlated Solution has been one of the greatest companies. They're the ones who sold us our infrared 3D DIC system. And we've been working directly with them and literally getting features added a feature last week that we needed to enable some of our tests. So through relationships with these third parties and these companies, it allows us to add these features that we need.
Sounds good. Okay. Raj, do you want to add anything toward the end here?
Thank you, Chris, and thank you, Dr. Stewart. I think at this point, there are a few questions that are left. It looks like Dr. Stewart's information is right in front of us. So I don't think he will mind if you follow up, but we're really grateful for everyone staying on a little over time. But this was a fantastic, very dynamic presentation. Lots of very useful leading edge information, Cal. So thank you so much.
Indeed. And thank you all for attending. Please, I encourage you to follow me on LinkedIn. I post what's going on in our lab every week, so you can stay up to date with the latest. And I am recruiting PhD students for next year in fall of 2025. So if you do have an interest, feel free to send me your CV for evaluation, as well as apply to our graduate program. Apply and make sure you mention my name in the prompt, in the application prompt, so I can find you.
Right. And then also mention that Dr. Stewart said this is the first time he found out about SAMPE. And thanks to Dr. Smith, you might consider joining the Materials for Extreme Environments Technical Committee. And everyone else on this call can also do that on the 365 SAMPE network. So thank you very much. Chris, any final remark?
No, I think I'm good. Appreciate everyone signing in, watching another good webinar, and hope everyone has a great afternoon or evening. Thank you.
Thank you, everyone. Thank you.
All right.
Bye.
Goodbye.
Bye-bye.
Goodbye.